Okay, in this lecture we're going to cover our section 3.3 material on arc length and curvature. So we'll talk about a few different topics related to vector functions or space curves throughout this section, and they've got some nice applications. So the first thing that we'll be talking about is the arc length of a space curve. So we've looked in Calculus 2 and 3 at a few different equations involving arc length. Say the arc length of a plane curve, arc length of a parametric curve, or a polar curve in the plane. So what about a curve in 3 dimensions, or a space curve? How can we determine its arc length? So we've got the following theorem, which we would call the arc length formula for space curves, which says the following. If we have a smooth curve C, defined by the vector function r of t, whose components are f, g, and h of t, where t is between a and b, then as long as this space curve C is traversed exactly once as t increases from a to b, so this restriction we're making is that this space curve doesn't double back over itself and trace out the same part more than once. Then its length is given by what we'll denote as lowercase s for arc length. And it's the integral of the magnitude of the tangent vector to this space curve, r prime of t, with respect to t on the interval from a to b. Or thinking about this in a little more detail, well, the tangent vector r prime of t, if we look at it, r prime of t is the vector whose components are the derivatives of our component functions. That is f, g, and h prime. Or if we're denoting these as x, y, and z of t, we would have the derivative of x, the derivative of y, and the derivative of z for our components. So taking the magnitude of this vector, well, the magnitude of a vector is defined by the square root of the sum of the squares of its components. So that is the square root of the sum of the derivative of our x component squared, our y component squared, and our z component squared. And this is being integrated over whatever interval that we're interested in, say from a to b. So these problems in arc length have some nice applications. Let's say that our space curve represents the position of some object moving through 3 dimensions over time, and we want to know, well, what's the total distance that our object has traveled in some time interval? Well, we would be calculating the arc length of that space curve over that time interval. So that's one practical application here. So let's look at an example of this. We're asked to find the arc length of the vector function given here on the interval from t equals 0 to 3. So using our new arc length formula, we would first find the tangent vector to this space curve, r prime of t. So differentiating each component, we would have 4t, and 3t squared. So for the arc length formula, we're supposed to look at the magnitude of this tangent vector, which would be the square root of the sum of the squares of these 3 components. So squaring our first component, we would have 16t squared, plus the second component squared would be 16t squared, and then plus our third component squared would be 9t to the 4th. Or collecting some like terms, we have the square root of 32t squared plus 9t to the 4th power. So our arc length of this curve S is given by the integral from a to b. In this example, t was ranging from 0 to 3, of the magnitude of this tangent vector, which we just found to be the square root of 32t squared plus 9t to the fourth dt. Now, in order to evaluate the antiderivative of this function, we first need to simplify our integrand. So if I factor out a t squared from the expression under the radical, I'm left with 32 plus 9t squared. And then taking the square root of that product, well, the square root of t squared is just t times the square root of our 32 plus 9t squared dt. Now, to evaluate this antiderivative, I can make use of a substitution. So if I let u equal 32 plus 9t squared, then du would be 18t dt. And if we change our limits of integration from t values to u values, let's see what we would have. So if our lower limit of integration was t equals 0, then u, which is 32 plus 9t squared, would be 32. And if t is equal to 3, our upper limit of integration, then u would be 32 plus 9 times 3 squared. So 9 times 9 would be 81, plus 32 gives us 113. So rewriting our arc length interval s in terms of the variable u, we would have the integral from 32 to 113 of the square root of u, and then our factor t times dt would be equal to 1 over 18 du. So I'm going to pull out the constant factor 1 over 18. We've got our du on the end. So for our antiderivative, we have 1 over 18 times the antiderivative of root u, which would be 2/3 u to the 3/2, which is being evaluated from 32 to 113. So finally, evaluating this expression, we have 1/18 times 2/3 gives us 1 over 27. Then when we evaluate u to the 3/2 at 113, we'll recall that the 3/2 power is the same as u times the square root of u. So we have 113 times the square root of 113 minus 32 times the square root of 32. All right. Now, the next thing that we'll introduce is an alternative way to parameterize curves, space curves in particular, in terms of arc length. So what we've been considering so far are space curves, which are the graphs of vector functions of the form r of t. So the variable or parameter t that we're using typically represents time. So we're sort of sketching out the graph of a space curve as maybe an object moves through time, but an alternative parameterization would be to consider the graph of our curve in terms of a vector function involving the arc length variable s. So we could maybe think about the position of our object in space in relation to the total distance that our object has traveled, or its arc length. So in order to do this, we're going to introduce what's called the arc length function. So let's start with some terminology here. Supposing that C is a piecewise smooth space curve defined by the vector function r of t, whose components are given as f, g, and h, where t is within some interval from a to b. We define what is called the arc length function as the function s of t, which would be defined as the integral from a to t of the magnitude of the tangent vector r prime of u with respect to u. Or again, that would be the same as the integral from a to t of the square root of the sum of these derivatives of our component functions squared. So this arc length function, s of t, geometrically represents the length of the part of our curve C between r of a, so here we're measuring the arc length starting at a up until some time t. So we're looking at the length of the part of our curve starting from the value a and going up until the value of our function at t. So to illustrate this, let's say, okay, we have this space curve C, looks something like this, indicating our orientation with these direction arrows. And we're looking at the part of this curve that starts from r of a. So when our variable t was equal to a, we have some initial point on our curve defined by this position vector. And then we're looking at the length of our curve up until we get to the parameter t, that is r of t, which would define some other point on our curve. So this arc length function is measuring the length along this section of curve from point A to point T on our curve. So this is what that s of t function represents. That is a function for how far our object has traveled over some time interval from A up until time t. Now, as I mentioned, when I started talking about this arc length function, it is sometimes useful to find an alternative parameterization of a curve in terms of its arc length, called an arc length parameterization. So for instance, if we have a curve defined by some parameter t, maybe time, and we know that the arc length function s of t is calculated or known, then I might be able to solve for the parameter t as a function of s. So that is, get time in terms of arc length and then reparameterize our curve in terms of the arc length variable s. So to make this a little more clear, let's look at an example of how this would work. So in our next example, we are asked to find the arc length function for the helix, defined by the vector function r of t, where t is non-negative, and then find an arc length parameterization of that vector function r of t. So the first thing I'm going to do is find my arc length function. So let me start by saying first, I'm going to calculate the arc length in terms of t. So our arc length function is given by the integral from our starting value of t, which in this example was 0, up until an arbitrary value t, of the square root of the sum of the squares of our derivatives. Now the derivative of our first component function would be -3 sine t. squaring that quantity, plus the derivative of our second component function would be 3 cosine t, squaring that quantity. And then the derivative of our third component function would be 4. We're squaring that value, and we're integrating here with respect to, oh, let's see, and I need to, since I'm using the variable t as my upper limit of integration, I need to use a different variable, let's say u, for the variable with my integrand. So here, if I have the integral from 0 to t, and I expand these expressions under the radical, I would have a 9 sine squared u plus 9 cosine squared u plus 4 squared, or 16, du. Then I find the sum of these first two squared terms would just be 9. If I factor out a 9 from each of those expressions, I'm left with sine squared u plus cosine squared of u, which is 1. So I really have the integral from 0 to t of root 9 plus 16 du. Now that is the integral from 0 to t of the square root of 25, or 5 du, which would give me 5t. So I found my arc length function. The total distance that I travel along this helix, starting at time 0 and moving forward, is equal to 5 times t. So we don't have units here. Let's say that we're measuring arc length in terms of maybe miles, in time t in terms of hours. So this says that the total distance traveled would be 5 times t. So after 1 hour, I will have traveled a total distance of 5 miles. After 2 hours, I'll have traveled a total distance of 10 miles, and so on. Now here, since s is equal to 5 times t, that means that if I were to solve for t, I would have s divided by 5. And if I were to look at the equation for my helix, r of t, in terms of s, since t is equal to s over 5, well, let's see what we would have for this vector function r in terms of the parameter s. Now, everywhere that I have a t, I'm just replacing it with s over 5. So I would have a 3 cosine of t, which would then be s over 5, 3 sine of t, which is s over 5, and then plus, or my last component was 4 times t, so that would be 4s over 5, or 4/5 of s. So this would be an alternative way to describe that helix in terms of the parameter s, which represents arc length, or the total distance traveled. So that is what's referred to as an arc length parameterization of a vector function. We find the arc length in terms of t, and if possible, we solve for t in terms of s, and then substitute that expression into our vector function to get a vector function in terms of the arc length s. Now, the next thing we're going to talk about in this section is the concept of curvature. Curvature of a curve, either in the plane or in space. Now, curvature is a measure of how, for lack of a better word, how curvy a curve is, or a little more specifically, how quickly the curve changes direction at a particular point. So more specifically, I'll say that we will define curvature to be the magnitude of the rate of change of the unit tangent vector with respect to the arc length of a curve. So let's think about this visually, just an intuitive idea here. So let's say that we have some space curve C sketched out here. So orientation is along this direction. And we're going to define curvature as follows. So let's look at the definition first and then we'll illustrate it. So here the curvature of a curve is defined as kappa. So we use kappa to denote curvature. And it is defined as the magnitude of the derivative of t, where t is the unit tangent vector, with respect to s, the arc length of our function. So if we think about tangent vectors to our curve, in particular unit tangent vectors, for any given point on our space curve C, we can find a unit tangent vector. So these vectors that I'm illustrating are unit vectors which lie tangent to the curve at a given point. And we're looking at how quickly these unit tangent vectors are changing as we're moving along the curve, that is with respect to arc length. So as we're traveling along this curve, we want to see how quickly these tangent vectors are changing direction. And we can see that for some parts of our curve, like as I'm moving along this section, my tangent vector isn't changing by all that much. And our curve appears to be pretty flat here. Now, when we start to move into this section of our curve, well, we see it is much more curvy, and therefore our tangent vectors are changing direction much more rapidly as we're moving along this curve. So this magnitude of the derivative of our unit tangent vector with respect to arc length is how we will define curvature formally. Now, when we're calculating the curvature of a space curve, we would not want to make use of this definition. Let's think about why not. So here, the formal definition of curvature is the following. Now, if we want to use this definition, I would first have to find the unit tangent vector for my space curve, that is t of t, which isn't too bad. We've seen some examples of that in our last section. But then I would have to find the arc length of, the arc length function of that unit tangent vector function in order to think about this unit tangent vector in terms of the variable s. So I would have to reparameterize my unit tangent vector function in terms of arc length and then take the derivative of that function and find its magnitude. Which becomes quite tedious. That would become a large amount of work here. So we do not want to use that approach. So what can we do? Well, we can make use of the following theorem, which gives us some alternative formulas for calculating curvature. So we have three together here. Our first one says if C is a smooth curve given by r of t, then the curvature, kappa, of that curve C at a given point is given by kappa of t, and it would be found as the fraction, or the ratio, of the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of our vector function. Now our second formula is the following. If C is a three-dimensional curve, so that is a space curve, then we can define the curvature as follows. Kappa of t would be given by the ratio of the magnitude of the cross product of the first and second derivatives of r of t, divided by the magnitude of the tangent vector r prime of t cubed. So this formula number 2 will be the formula that we use most frequently to calculate curvature of a space curve. And in our third formula, we have a special case if our curve C is the graph of a function of the form y equals f of x. So that is a plane curve in the xy plane, and both y prime and y double prime exist. Then the curvature kappa at any point xy on our curve is given by kappa of x, which would be the absolute value of the second derivative of the function which defines our curve, divided by 1 plus the derivative of that function squared, all raised to the 3/2 power. So now that we've discussed curvature, what it represents, and some ways to find this, let's look at some examples. So in this next one, we are asked to find the curvature of a curve called the twisted cubic, which is the graph of this vector function t squared, t cubed, at a general point and at the origin, 0, 0, 0. So here we have a space curve, since this was a three-dimensional vector function. So to calculate the curvature, I'm going to make use of that formula number 2 from our previous theorem. Now, to make use of that formula, I first need to calculate a few things. So let me start by saying first, I need to find r prime of t for this vector function, which would be 1, 2t, 3t squared. And I need the second derivative of this vector function, r double prime t, which would be 0, 2, 16. So to make use of that formula, I then need to calculate the cross product of r prime and r double prime, which would be given by the determinant of the 3x3 matrix whose first row consists of our standard basis vectors I, j, and k. The second row would be the entries from r prime, 1, 2t, and 3t squared. And our third row would be the entries of r double prime. So finding this cross product, our I component, would be given by 12t squared minus 6t squared, so 6t squared. Our j component would be given by 0 minus 6t, so negative 6t. And our k component would be given by 2 minus 0, or 2. Now the next thing that I need to find for that curvature formula is the magnitude of this cross product of r prime and r double prime. So that would be the square root of the sum of the squares of these components. So taking 6t squared and squaring it, I would have 36t to the fourth, plus the negative 6t squared would give me a 36t squared, plus 2 squared, which is 4. Or if I factor out a 4 from each of these terms, I would have the square root of 4, or 2 times the square root of 9t to the fourth, plus 9t squared, plus 1. And I also need to calculate the magnitude of r prime of t for that formula, which would be given by the square root of the sum of the squares of my components from r prime. So looking back at what we had for r prime, our first component was 1, So 1 squared is 1, plus our second component, 2t squared, would give me 4t squared. And then my third component, 3t squared, quantity squared, would give me 9t to the fourth. So at this stage, we're ready to calculate the curvature, kappa of t. And it's given by the magnitude of the cross product of r prime and r double prime, which we found to be twice the square root of 9t to the fourth plus 9t squared plus 1 over the magnitude of r prime raised to the third power, or the magnitude of r prime cubed. So I would have this radical expression cubed, which I could then rewrite as 1 plus 4t squared plus 9t to the fourth. This square root expression would be the 1/2 power, and then cubing that would give me the 3/2 power. So this would be the curvature, kappa, in terms of t, so that is the curvature at some arbitrary or general point along my curve. And then we also wanted the curvature at the origin, 0, 0, 0. Now, for this twisted cubic, the origin, 0, 0, 0, corresponds to a value of t equals 0. In order to get the vector, 0, 0, 0, I see that t would have to be 0. So let me say the following. At the origin, I know that t has to be 0, and so the curvature at the origin would be found by taking the expression that we just found for curvature and substituting in t equals 0, which leaves me with 2 over 1, or simply 2. All right. Now let's look at another example, slightly different. Here we are asked to find the curvature of the plane curve, y equals cosine x, at a general point and at the point 0, 1. So using the formula number 3 from our previous theorem for alternative forms of arc length, we would first need to calculate the first and second derivatives of this function, which define my curve. So here my function was f of x equals cosine x. So taking its first derivative, I would have negative sine x. And the second derivative, f double prime x, would be negative cosine x. So our curvature, kappa, at some point x, is given by the absolute value of the second derivative, which was negative cosine x, over 1 plus the first derivative, which was negative sine x squared, all raised to the 3/2 power. So this gives us, well, our numerator, the absolute value of negative cosine x, is the same as the absolute value of just cosine x. And then our denominator is 1 plus sine x squared, all raised to the 3/2 power. So this would be our expression for the curvature at a general point. And at the point 0, 1, well, we just found an expression for the curvature in terms of a general point x. At the point 0, 1, x is 0. So for that point, we would substitute 0 in place of x, and we would have the absolute value of cosine of 0, which is 1, over 1 plus sine of 0 squared, which would be 0, all raised to the 3/2 power. So 1 over 1 would just be 1. All right. So we've got a few different ways to calculate curvature, depending on whether we're working with a plane curve or a space curve. And again, these quantities that we're finding for curvature are a measure of how quickly the unit tangent vector is changing direction with respect to arc length, or more intuitively, a measure of how curvy our space curve is at a particular point. Now, the next thing that we're going to talk about in this section are special vectors associated with a space curve in 3 dimensions, some of which, or well, one of which we've already talked about, the unit tangent vector. Now recall that the unit tangent vector t of t was defined as a unit vector that is tangent to our curve at a point. Now some other vectors which we'll define that will go together with the unit tangent vector are called the principal unit normal vector, or sometimes just the unit normal vector for short. And this would be the vector denoted as n of t, and it's defined as the derivative of the unit tangent vector, t of t, divided by its magnitude. So this, of course, gives us a unit vector, which is lying orthogonal to our, or tangent to the unit tangent vector. So here, to illustrate, as we're going through these definitions, let's say that we have a space curve, C, sketched out here. And let's say its orientation is in this direction. So recall the unit tangent vector for a point on a curve is a unit vector which lies tangent to our curve at that point. So vector of length 1 tangent to the curve. So this principal unit normal vector is the vector n of t, which lies orthogonal to that unit tangent vector t of t and has length 1. So it would be illustrated here. It is orthogonal to the curve itself. So here we say it is orthogonal to our unit tangent vector. Now another vector that we can define is called the binormal vector, which would be the vector denoted as capital B of t, and it's defined as the cross product of the unit tangent vector and the unit normal vector. So of course we've seen one property of the cross product is that the cross product of 2 vectors is a vector which is orthogonal to both the unit tangent vector and the unit normal vector, the 2 vectors I was taking the cross product of. So on our curve here, taking the cross product of those 2 vectors, we get this b of t vector called the binormal vector. So notice from our illustration here that these 3 vectors, the unit tangent, the unit normal, and the binormal vectors, form an orthogonal set of vectors, which is sometimes called a Frenet frame that moves along the curve as t varies. Now this Frenet frame has some nice applications in fields called differential geometry, or in studying the motion of spacecraft in 3 dimensions. It provides a sort of point of, or frame of reference for an object moving through 3 dimensions at any given point along its trajectory, or this space curve, C. So let's look at an example of calculating these vectors which make up the Frenet frame. So here we are asked to find the unit tangent, the unit normal, and the binormal vectors for the helix defined by r of t, which is given here. So in order to find our unit tangent vector, we first have to find the tangent vector to our curve, so that is the derivative of this vector function, which would have components negative sine t, cosine t, and 1. And then I need to normalize this vector so that it has length 1. So I need to find its magnitude, which would be given by the square root of negative sine of t squared, which would be sine squared t, plus cosine of t squared, which is cosine squared t, plus 1 squared, which is 1. Or since sine squared plus cosine squared of t is equal to 1, we're left with the square root of 1 plus 1, or root 2. So our unit tangent vector, capital T of t, is the vector negative sine t divided by the magnitude root 2, cosine of t divided by our magnitude root 2, and 1 over root 2. So we found our unit tangent vector, which was the first thing we were asked about. The next thing that we're asked for is the unit normal vector. Now to find the unit normal vector, we need to differentiate our unit tangent vector. So let's look at capital T prime of t. So differentiating our components, we will have negative cosine of t over root 2, negative sine t over root 2, and 0. So we then need to normalize this vector by making sure it has length 1. So I'm going to calculate the magnitude of this vector. So moving down to give ourselves a little more room, the magnitude of this t prime of t vector will be the square root of the sum of the squares of our components. So squaring our first component, well, negative cosine t squared gives us positive cosine t squared, divided by the square root of 2 squared would be 2. Then plus for our second term, negative sine of t squared would be sine squared t, divided by the square root of 2 squared is 2, and then plus 0 squared is 0. So we're left with sine squared t plus cosine squared of t, which is 1 over 2. So we've got the square root of 1/2, or 1 over root 2. So the unit normal vector n of t is found by taking the derivative of our unit tangent vector and dividing by its magnitude, which was 1 over root 2. Now dividing by 1 over root 2 is the same as multiplying by root 2. So we're left with the vector negative cosine t, negative sine t, and 0. And the last thing that we're asked for was the binormal vector, which would be the cross product of our unit tangent and unit normal vectors. So let's take a look. Looking at the binormal vector b of t, we would take the cross product of our unit tangent and unit normal vectors. So this would be given by the determinant of a 3x3 matrix whose first row consists of our standard basis vectors I, j, k. The second row would be the entries from our unit tangent vector, which were negative sine t over root 2, cosine t over root 2, and 1 over root 2. And then the last row would be the entries of our normal vector, which were negative cosine t, negative sine t, and 0. So for this cross product, looking at our I component, we would have 0 minus negative sine t over root 2. So we've got a sine t over root 2. Our j component would be negative cosine t over root 2 minus 0. So negative cosine t over root 2. And our k component would be sine squared of t over root 2 plus cosine squared of t over root 2. So the sine squared plus cosine squared gives us 1 over that root 2. So this would be our binormal vector. Okay. Now to finish out this section, we will define 2 planes that are related to a space curve, which are defined by a couple of vectors within the Frenet frame. So let's consider these particular planes of interest. So here we would say that the plane determined by the normal and the binormal vectors in and b at a point P on a curve C is called the normal plane of that curve at the point P. And I say that the unit tangent vector is the vector orthogonal to that normal plane. So to illustrate this normal plane, let's look back at our figure where we were illustrating this Frenet frame. So I claimed that the normal plane is the plane determined by the normal and the binormal vectors. So let me illustrate that with a different color here. So if I consider the plane that contains the normal vector and the binormal vector, so think about a plane extending infinitely containing these 2 vectors, we have what's called the normal plane to our curve. And we can see that for any point on our curve, let's say this point P that we're considering for these vectors, we can see that our curve would be orthogonal to that normal plane, or the curve is normal to the normal plane, hence the name normal plane. And now if we're interested in finding the equation of that plane, well, we need a point that the plane passes through, which would be our point on the curve, and we need a vector that is normal or orthogonal to that plane. And we can see from our figure here that the unit tangent vector t of t would be orthogonal to that normal plane. So that was summarized in our discussion here. The unit tangent vector is orthogonal to our normal plane. Now another plane that we could define would be the plane determined by the unit tangent and the unit normal vectors t and n. And this plane is called the oscillating plane of the curve C at a point P. And for this plane, the binormal vector is orthogonal to that oscillating plane. So to illustrate it, let's look back at our figure here. So the oscillating plane is determined by the unit tangent vector and the normal vector, or unit normal vector. So it would be the plane, think about this plane extending infinitely in all directions, which lies sort of flat on top of our curve at a given point. So this plane is again our oscillating plane. And the vector b of t is of course normal to that plane. So let's look at an example of calculating the equations for these normal or oscillating planes to a curve. So in this next example, we ask for the equations of the normal plane and the oscillating plane of the twisted cubic, defined by r of t as t squared, and t cubed, same curve we were looking at earlier, at the point 1, 1, 1. So there's a couple of things we need here. First, let's consider how we would find our normal plane. So the normal plane has a orthogonal vector given by the unit tangent vector. So I want a vector that is pointing in the same direction as the unit tangent vector, which I will use as the normal vector to this normal plane. Now, to get a vector in the direction of the unit tangent vector, well, I can take any old tangent vector. That is the derivative of my vector function, which would give me a vector that lies tangent to my curve at any point. So here, our derivative would be 1, 2t, and 3t squared. And I'm interested in this plane at a particular point, at the point 1, 1, 1, which corresponds to a value of t equals to 1. So the only way that our vector function can equal 1, 1, 1 is if t is 1 itself. So if we look at the tangent vector at t equals 1, we would have the vector 1, 2, 3. So I now have a vector which lies tangent to the curve and therefore is normal to the normal plane at the point 1, 1, 1, and I have a point that my plane passes through. So I can then find the equation of my normal plane. Let's find it. So here, the normal plane is given by, so we take the first component of the normal vector to that normal plane, which was our tangent vector here. Its first component was 1, times x minus the x coordinate for our point on the plane, plus the second component of our normal vector, which was 2, times y minus the y coordinate for our point on the plane, 1, plus the third component for that normal vector, which was 3, times z minus the z component from our point on the plane, which was 1, and that has to equal 0. So we find that x minus 1 plus 2y minus 2 plus 3z minus 3 is 0, or grouping the constants together, we have x plus 2y plus 3z minus 6 is 0, or the sum of these values is equal to 6. Now, in order to find our oscillating plane, well, the oscillating plane has a normal vector given by the binormal vector. So I want a vector that will be pointing in the same direction or is parallel to my binormal vector. And the binormal is defined as the cross product of the unit tangent and the unit normal vectors. So to get a vector pointing in that same direction, let's take the cross product of a tangent vector to our curve, that it would be r prime, and the second derivative, r double prime of t, to get a vector pointing in the same direction as the unit normal vector. So here, let me say, well, we already have r prime of t. I need r double prime of t, which would be 0 to 16. And this second derivative, r double prime at our point of interest, 1, 1, 1, which corresponds to t equals 1, would be the vector 0 to 6. So I'm going to take the cross product of r prime of 1 with r double prime of 1 to get my vector, which will be normal to the oscillating plane. So here we have the cross product of of two vectors in 3 dimensions, which is given by the determinant of the 3 by 3 matrix, whose first row is the standard basis vectors, I, j, k, Our second row would be r prime of 1, which was 1, 2, 3. And our third row would be r double prime of 1, which was 0, 2, 6. So taking this cross product, we have our I component would be 12 minus 6, or 6. Our j component would be 0 minus 6. And our k component would be 2 minus 0. So the oscillating plane is given by the equation 6 times x minus the x coordinate for our point, which was 1, plus our next component, negative 6 times y minus 1, plus the third component, which was 2 times z minus 1, is equal to 0. So simplifying a little, we have 6x minus 6 minus 6y plus 6 plus 2z minus 2 is 0. So we're left with 6x minus 6y plus 2z is equal to 2. Or dividing both sides of this equation through by 2, we have 3x minus 3y plus z is equal to 1.